Good afternoon, everyone. It's 10 minutes after 4, so I think since everyone is here, we can get started. We will be hearing today from Dr. Naira Hovakimyan. Dr. Hovakimyan is a professor of mechanical engineering at the University of Illinois in Urbana-Champaign. She has co-authored 2 books, 6 patents, and over 450 publications. She's won numerous awards and is a fellow at the IEEE and the AIAA. She conducts research in control and optimization, autonomous systems, neural networks, game theory, and applications in a whole range of studies. And she will be speaking today on aerial co-robots of the future. So without further ado, please join me in giving a warm welcome to Dr. Hovakimyan.
Thank you for having me here, and thank you for being so enthusiastic and maybe interested in this talk late 4 p.m. Friday. So I appreciate everybody's presence and attention. So this is a talk that I have given last year in AIAA Guidance, Navigation and Control Conference plenary when I was asked to do plenary on the drones. I thought that what are the topics that today interest the researchers in this field? And I came up with these 3 distinct themes. It's safety, intelligence, and certification. Any research that I look through, it touches upon one of these 3 topics in large. So what do we mean by safety? By safety, we mean that they have to be safe no matter what. It's kind of almost a binary response, right? If there is a flying technology here in the room and it's not safe, we don't want to see it, even if there are lots of promises that it can do some task, deliver a job or what. So safety is binary, so it's either safe or not safe, and it's not safe, we don't want it. When we talk about intelligence, then there are different levels of intelligence, starting from vacuum cleaners in our homes that do simple jobs, and growing up to autonomous space assembly, that's very complex tasks. So these are different levels of intelligence that we're working on to build it. Certification, what does certification mean? Certification is needed so that we can scale the technology and generate economic impact. If we think of the flying technologies in the previous century, we used to refer to them as unmanned aerial vehicles, UAVs. All of a sudden, by the 21st century, we call them co-robots. Why? Because we want them to operate around humans and solve different tasks along with humans and have societal benefits, right? We want to scale them to consumer markets. If we want to scale a technology to consumer markets, it has to be affordable so that it can scale and generate economic benefits, generate wealth. For that, we need to come up with new paradigms of certification. The old paradigms of certification that were used to certify the super expensive aerospace industry technologies will not help us to hit the consumer markets. So that's why I kind of isolated these 3 topics, and as I motivated with the transition between the 20th and 21st centuries, how we moved from unmanned aerial vehicles to aerial co-robots, here are the kind of challenges that the 21st century forces us to face, right? We have overpopulation. By 2050, we'll have to feed 10 billion people. With today's farming technology, this appears to be impossible. We are now building this powerful technology of digital agriculture that uses satellite data, airplane data, drone data, and different type of data layers to generate technologies that can help farmers to get insights about the crop condition and to take timely actions, right? We need new types of flying technologies to achieve these goals. We're talking about global warming, right? We're talking about food deprivation. We're talking about premature deaths due to pollution and everything. And the car ownership is just killing us, right? It just grows exponentially. We need to think of new means, out-of-box paradigms, how to reduce, how to get a relief from this. So if we look into the future, we can see today like the Hyperloop, so we're trying to ease the transportation by going under the earth. We are exploring new types of space technologies to improve the communication, to support everything. But if we look through these 3 layers, basically the low altitude flight of aerial vehicles seem to be the most scary because it has to transport people and it has to be safe, right? So it's very important to understand the challenges that need to be solved on this level. Some of the game-changing impact that we expect to see from these flying technologies involve agriculture, right? So if the price goes too high, the farmer will never pay. That's why it has to be affordable. So helping the firefighters, so it has to be safe, intelligent, to figure out different layers of data here, cooperate in the presence of fire. It has to do partial delivery, so people have to be kind of feel safe when the drone approaches them to deliver something. We see the aerial highways that the flying cars will fly. So this type of vision kind of requires us to think very seriously how we develop this new technology.
It happened just this afternoon, a very close call between a drone and an airliner on approach to New York's Kennedy Airport with 159 people on board.
Anyway, this was a really scary thing, a narrow miss.
Investigators believe a faulty sensor that had failed on 3 previous flights triggered.
And in an instant, the 33 drone fleet was reduced by 1. The unmanned plane crashed.
Yeah, here you can see its horrific explosion rating. Now, the rocket split out of control in several phases.
So basically what we say that, safety and intelligence must be built into design principles from day one so that the aerial robots can safely coexist with humans. It would be enough to have one crash, one catastrophic failure, and it can put all of us back for kind of a few decades. So I started from the last century where we saw the huge progress in aerospace industry, starting from Wright brothers' flight in 1903 up to developing space exploration vehicles, commercial airliners that transported people, and with all the emphasis on consistency, safety, and profitability, so certification costs were just skyrocketing, right? Now we're moving towards small, collaborative, human-centered, reconfigurable technologies that require new type of paradigms of how we formulate the problems in this data-driven world. And we need lots of talent and the technology expertise to be transitioned from the big industry to building these new technologies in a safer world. But that requires us also to face the certification challenges that the big industry imposes, right? The three pillars that I identified in this talk, and some of the problems that our group works on, so I would split into these topics of safety, intelligence, and certification. And we naturally borrow ideas from classical control, from machine learning, from information theory. Without the classical results, we can't move forward. This is very important to understand how we teach the students the foundations of classical disciplines that form that give us the opportunity to tackle these problems rigorously. So from the perspective of safety, what did we do in our group? So we worked a lot on robust flight control. We work on collision avoidance problems, respecting some constraints because some of these systems have to operate in the presence of constraints like aerial refueling, so they have timing requirements, special constraints, how to approach and handle it. And we worked also on some cybersecurity problems that I would tackle. So L1 adaptive control, so if some of you have not heard of it, it's a type of control methodology that we developed over the last 15 years. We got the opportunity to commercialize it across a few industries, and we were also able to fly it on Learjet and F-16 that I will shortly introduce. Here is a brief timeline how quickly we developed it. So the key success that came from testing the 5.5% Boeing 757 at NASA, where it was the only controller cleared by the pilots for stall and post-stall flight regimes, and where it gave complete controllability to the pilot for safe recovery. Later, we got the opportunity to fly it on Learjet and F-16 with people on board, which was considered to be a great kind of breakthrough because, aerospace industry is very conservative regarding testing new methods, especially when people are on board. But we kind of cleared lots of check marks to get to that point over the 10 years. And the airplane we get to test is this Learjet, Calspan's Learjet. It has variable stability system. Basically, they can inject artificial dynamics to put the airplane into accident, and the switches will come on to save the airplane, unless you bring in the controller to save. So this opportunity I get thanks to one of my former students from Virginia Tech, who is a test pilot school instructor at Edwards Air Force Base. Here is a type of flight test that I will turn on now. So the pilots are asked to do Cooper-Harper ratings. What are Cooper-Harper ratings? So if you're flying in a safe airplane and there is no fasten seatbelt sign, it's called flying qualities level 1. If there is a little bit disturbance with fasten seatbelt, it's called flying qualities level 2. So the students that fly to test the controller, they are asked to give ranking. They have basically a big sheet in front of their eyes that they have to look and say, oh, the accident put us into flying qualities level 4 and the controller helped us to recover up to level 2. So this sheet in their eyes, they are trying to do the CHR testing, you will hear in the video, and they are saying it's impossible to read, it shakes too much, turn on the controller so that we recover. This is a little bit funny movie. And then by the end they go for landing, and when they go for landing you will hear the expression they like to say, uneventful, very uneventful. You'll see now a small episode how life is constructed in Edwards Air Force Base for pilots. So this is initially not engaged.
Constantly overshooting my desired bank though. Jason's writing live right now.
Yep.
You're running around 27. I'd recommend you just do the task with L1 on and don't do both. But
Got it. All right, so you did not get adequate on that one?
Okay.
Okay, so if you want to run through a CHR real quick, you did not get adequate. So we're starting in.
Can I get L1 on as we do the
Yep.
there's your answer, right?
All right, Ellen's coming on in 3, 2, 1. Now Ellen is on.
Thank you. Rush, if you didn't ask, I was gonna.
So basically she asked to do the CHR testing, they asked for the controller to stabilize to wait. And now they go for landing. Landing is going to be the most complicated of all the tasks that the pilots do. But with landing, they're extremely careful to take risks. But here they go for that, and there is a lack of dynamics injected. So they go for landing. You'll hear, you've got the airplane. And it says,
You see that?
Yep.
I've got the airplane, so land it. Very uneventful. So basically, we got some media from here in Aviation Week, and then in 2016 we flew the F-16, which we cannot show, but in 2018 we got more challenging scenarios to be tested, again on Learjet. So they do model upgrades every time, so every other year we get the other airplane. And this is some accident that happened in 1967, from which actually the pilots survived, but they are able to inject these dynamics into this airplane and to get the same level of oscillations and turn on the controller to see how much we recover. What I want you to pay attention, when the controller gets injected, it recovers with some leftover residual dynamics. This is what I tell my students, 0 is an ideal number. It doesn't exist in real world. In real world there's always some leftover. So just pay attention now. So there's no controller, so the safety switches come on.
I can't even control the airplane. Do you have your airplane?
So the safety switch came on and shut down the accident that's injected. And now they inject the failure with our controller on. You listen, 3, 2, 1, they inject.
Okay, task in 3, 2, 1. Now?
There's some underlying oscillation left. It's
So you
very,
can feel there in high frequency. I made some high frequency inputs, excited the roll. Lower frequency, the roll, overshoot, or oscillation tendency is less.
Sounds good.
There's still some there.
there's still
Pitch,
something.
I'm having no issues. Fine tracking and gross tracking are very good at pitch.
All right, I have maneuver complete.
So basically there's always something left, right? What we mathematically prove converges to 0. In reality there is always the leftover. And we never aim to get rid of it. That gives you the
All
sense
right,
of reality.
reporting on in ready, tack.
Running.
Now they shut down the
Way
engine.
back. Left hands up. 3, 2, 1. Now. Controls fixed. And recover, please.
20-degree degradation.
Cars back.
Now the pilot tries to control and he brings it to 12-degree degradation. Then we come with our
And I'm ready to
controller.
try this now with you, with a pilot correcting for it, so.
Okay, and I'll give it about 1 second reaction time. I am on conditions.
All right, and then recording on my call, ready, pack.
On. Okay, power, it'll be left throttle. Okay, in 3, 2, 1, now. One potato, and recover.
And recording off.
Okay, recording off, matching cloth.
And now with our controller without the pilot, we get to 3
Okay, I'm ready
degrees.
for the recording on ready, pack.
Okay, left throttle coming back in 3, 2, 1, now. I'm not touching the controls. Nice demonstration. Yeah, check that out. About 3 degrees of left bank. Speeding in the rudder to match. I can feel that. It is descending a little bit, but it's descending a bit, but that would be easy to compensate for. Yeah. Okay. I think you got some good data there.
All right, recording off.
Matching power, recording's coming off.
So basically these flight test opportunities give the students to test the theoretical results that we developed, to understand how challenging it is to go through this experience with the pilot, and to understand that in real world there is really never a perfect zero. It's always, there's going to be something, no matter what we prove, but to understand how to map the theoretical world to the real world, this is a kind of a golden experience that we have. So again, we got some kind of media press here. And as I said, we bring these technologies into the world of real world problems, right? We want to address multi-vehicle missions. We want to help with parcel delivery, with search and rescue, with different types of air sampling missions, something that we do at NASA. And here is where we have to address different temporal and spatial constraints simultaneously. When we talk of aerial show, right, all that matters there is the configuration. For example, the time is irrelevant. They fly 2 p.m., 5 p.m. I mean, the absolute time is irrelevant here as long as they maintain the configuration. But when they have to come and do sequential auto landing on a ship, it's not like that. As they get close, the temporal and spatial constraints change. When they are far, they are more relaxed. So how to address these different types of multi-vehicle missions that have different temporal and spatial constraints to be respected in different cases. For that, we have this fundamental idea borrowed from 1973 paper of French researchers. It has to do with decoupling of space and time. So we decouple space and time in the problem formulation so that we do the path following using a geometric approach while we address the coordination constraints, the temporal constraints, through velocity adjustment, right? Basically, if they don't talk to each other, they will end up with a coordination constraint, but they can talk to each other and achieve simultaneously. So this is achieved with the help of this architecture, where basically the block in blue generates a path and the velocity profile, and the path following is done using geometric approach, while the velocity profile is used for adjusting over a network of communication to achieve the desired coordination constraint, the temporal constraint, right? And we have a book here as well. So here is a nice test done at NASA Langley, where the 2 drones fly through a maze to demonstrate how through coordination of their velocities they can achieve simultaneous landing. The two drones take off from the right, they go through the maze, and at the same time they talk to each other. And there is path shaping. Of course, they have a rough model of the maze because these are small drones. They cannot carry big CPU to do everything in real time. They have a model of the maze, a rough path, but they do silhouette-based path shaping, and they coordinate with each other. This is just to demonstrate the coordination, the velocity adjustment, that they come and land simultaneously. This is a NASA Langley facility. They come and land simultaneously at the same spot where they started the flight. And this experiment we have done with UAVs in Camp Roberts, California for search and rescue missions. It's on our webpage. We have done it with different drones in the lab, Dancing Tango, that I've not included it in this presentation for time reasons. So, and we get this here. And hold on. This is another fast collision detection algorithm for detecting collisions with super fast methods. We use again some geometric methods, GJK algorithm with Decastel-Joule, how to split the curve and compute the proximity to the obstacle to avoid. And again, these some geometric methods help us to beat on the computational speed, basically, for past collision checks. And this kind of results are very important in self-driving car industry, where a pedestrian can suddenly pop up or another obstacle, and you should be able to quickly detect your collision probability and avoid them. So the speed of computation is very important. As I said, we have worked also in cybersecurity, and here what we do, so understanding that as a control community, we work on this robustness problem to be robust towards component failures, disturbances. We always assume that the software is correct. At the same time, the CS community has lots of methods for software robustness, assuming there are no changes in the dynamics. So what we did, we came up with a reduced stability envelope within which we can be robust to both component failures, disturbances, and also to software failures. So this came along with L1 simplex architecture in collaboration with Louis Shah at University of Illinois, and we implemented it again on a drone that we fly now in the lab. There are special zero dynamics attacks that we inject, and you will see how the drone fails. While with this multi-rate approach, we are able to save it from failures. So say the attacker knows how to attack at what frequency to generate instability. And you will see how, because of the attack command cannot be detected at that sampling time. So we have a multi-rate version of our controller that would help to avoid this type of crash. Now you will see. The drone is flying there, and the attack signal is activated, and the drone was saved. And now we show that if we do not do the multi-rate, we won't be able to save. Even with our super powerful L1 controller, it will crash if we do not go for the multi-rate implementation. Here are the two side-by-side figures. So the one crashes and this one survives. So we can go forward. And as I said, today we work in a world where we want these aerial co-robots to help people with some tasks. So we need them to be capable of processing different data, understanding what the people need, and to be helpful, like parcel delivery, like safe intelligent control for self-driving cars, to be able to process obstacles, pedestrians, and so on. For that, so it's very important to understand what are we dealing with. We are dealing with a world full of data that we need to understand and estimate what's missing, right? For example, if a drone flies high altitude, it has top view, it has complete observation. But with a frontal view, it has only partial observation, so it needs to estimate some of the missing information. So how we do it? So we have a method where we have combined the Q-learning with hidden Markov models, right? And we have come up with a scheme that allows us to do estimation, basically, to achieve the same performance of the full state observation. Like you see here, the proposed method with the gray that it shows up, it achieves the level of estimation that one would have had with full state. So I don't want to go through the mathematical details of it, because if you do not have the background, it might be hard to follow. But we can go through this Unity simulator where we simulate the two UAVs in a collaborative task. One flies high altitude, has good vision of the environment, and helps another UAV that flies low altitude with partial vision to find the pedestrian and to approach the pedestrian. So this Unity environment is also a good environment that helps to do nice simulations and test different ideas and have nice illustrations. So this looks down, finds the person, communicates with the other agent, and the other agent approaches the person slowly. Here is some kind of, you see, random search because of the reinforcement learning iterates. These are RL iterations a little bit around it, right? So if we move forward, I said in the beginning that we deal with this perceived safety. So what you see here, the student has trained this drone to come and stop within half a meter from him. But every time the drone approaches, he's still scared. What does it mean? It means that the perceived safety of humans is not equivalent to actual safety. He knows it's going to be safe, but he's scared. This is the human reaction. So apparently psychologists know how to assess humans' anxiety level and when to judge whether the person is scared or not. They have their own machine learning machinery to do that. But the most important thing, they know how to do these experiments. Basically, they help us to conduct experiments in VR. This is virtual reality, where we measure certain signals, and I'll show it on the next slide, to judge whether the person feels safe or not. And these signals that we measure, the signals that we measure are skin conductance, heart rate, and head tilt. Apparently, with these three signals, the psychologist can judge whether the human is stressed, scared, or not. Because if we ignore this fundamental question, we won't be able to bring the drones to the society and help people. There will be lots of mistrust. If people don't trust, they don't accept, okay? And for this acceptability, we had to go through this research. Basically, here we show just the signals that we measure, the skin conductance, heart rate, and head tilt, like you see my student wears this technology, and in a VR he experiences different drones coming, and as we measure the physiological arousal and head tracking, we are able to say whether the human is scared or not. So what happens here, as you work with psychologists, this is across the disciplines, the social scientists have different metrics for measuring. If they get 30% accuracy from social surveys, it's considered to be cool and super good for them. For us engineers, it's not good. For example, there are linear regression methods for kind of building these machine learning models. Show here that yellow area that the person is still aroused while the drone is far. Like you see, when the drone approaches 0, if you look at the vertical here, right? So my finger doesn't flow. So this shows the drone distance from person. If the drone gets close, the person is aroused. The drone gets close, person is aroused. Here the drone is far, but the person is still aroused. So then we started working with them to understand how this happens. And the person may be daydreaming or maybe anticipating the drone coming close and gets aroused while the drone is far. So how to disregard these samples which are noise from our perspective? We don't want to learn that and to improve the likelihood of detecting the drone's closeness. So we came up with the latent variable model to take into account humans' attention that helped us to kind of be more sophisticated and to improve our machine learning by 4 times. So here is the path. So if the drone comes to drop a package behind the human, he will follow the blue path not to scare the human, whereas the green is the minimal length path. And as he passes the visual field of view of the human, he can accelerate. If the drone comes to deliver something to you, he will have just to slow down the drone so that you are not scared. Because if he comes past, the people are more scared apparently by the velocity profile than by the geometric size. That's also already something that the psychologists apparently know very well because they have done these experiments in VR. So, and by building this machine learning model, for which we need to do lots of offline tests, right? You can't build a machine learning model of humans' anxiety in real time. It's just not realistic. We are talking here about safety. We just have to have lots of data, lots of experiments in VR, build this model. But then as we build this model and the drone is following, it can do path replanning in real time. This is what we show here, that you can do real-time path replanning around the humans, still using the same machine learning model, because that you cannot update in real time, but you can avoid the humans and adjust the path and be safe. And here we employ model predictive path integral controller kind of to do path adjustment around the human. So the drone comes, it's again VR, so VR appears to be very convenient environment these days to test these type of paradigms across different disciplines. And we are lucky just to have this collaborator from psychology who understands how to conduct this experiment, what data to take. We call it socially aware motion planning. So if we want the drones to come into society and help us with different tasks, they have to have this socially aware motion planning framework to be able to operate around us with safety. So how safe we can be. Certain things we can't update in real time, like human safety perception model. This has to be done offline and sitting there. But path replanning can be done in real time with available tools that we have, right? So now we want to have kind of AI embedded with control. So the reality is that AI tools, they are intelligent, they can learn certain things, right? But they're not safe because we don't know how to certify the AI technologies. Instead, we have the control, classical control, for example, which is reliable and safe, but it has no intelligence to it. So how do we combine intelligence with safety? These are the types of challenges that today, I guess, all of us are facing. And we're working with Georgia Tech, with Evangelos Theodorou. So he has this self-driving car on the dirt track that you see here. So basically, we're combining the uncertainty quantification methods with expert controllers so that when your uncertainty quantification exceeds a certain threshold, you switch back to your safety controller to guarantee your safety. And we have here some project with NASA on their urban-aided mobility project where we're trying to bring these things to some flying cars. So a fundamental dilemma that we're coming to is how to ensure certifiability at affordable cost. As I said, the conventional aerospace industry that has developed these certifiable airplanes that were flying safely over the oceans is super expensive. They go through wind tunnel, they build models, they spend years and years to build Boeing, say, 787, costs who knows how many millions, and we're flying safely. If we spend the same level of effort in wind tunnels for the small UAVs, drones, we won't be able to bring them to consumer markets. The farmer will never pay, I don't know, $1,000 for getting the diagnostics of his farm. To make it affordable, so we need to find some modern tools to make certification easier. If you remember the body lecture of 1989, so Respect the Unstable, so Gunther Stein had a good quote. He said, control communities lucky. We have conservation laws that help us to be humble. Conservation laws, we know very well how to trade off robustness for performance, and that's what lies at the heart of certification of expensive aerospace industry. They use gain and phase margins to certify flight control laws. But the modern AI methods kind of seem to lack this type of well-established conservation laws. The AI community today says, give us all the labels, all the data, the super powerful computers, we can understand, learn, identify everything. So unless we figure out what are the conservation laws in the mainstream AI thinking, it might be very hard to certify the AI technology. Conservation laws are very important. And if we look again into this traditional certification of present flight control technologies for gain and phase margin, and we switch to the future technology, we need new paradigms that would account for uncertainty quantification using probabilistic measures, because uncertainty can never be quantified deterministically, that account for human factors, that will be humans around us, and they need to take into consideration the economic aspect so that it becomes affordable. Right? It has to be trustable, humans have to trust, it has to be economic, affordable, so that it becomes societal benefit. So we had three interesting applications in our lab that I briefly touched base. One is helping elderly. So it's projected that by 2040, the elderly population will double, which means that the assisted living facilities will be short of young people to help elderly. Elderly people prefer to age at a place where they know everything around their house, and there can be some small technology helping them, finding missing glasses, picking up the fallen fork from the floor, bringing them a pill, finding a remote control for the TV. And here is something we demonstrate here. cartoon that everybody has seen. So it's not that much about a box, right? So this they call for cooperation. Communication, now they call people. So she could say. So these are the questions we're trying to So, I mean, don't laugh, these questions exist, right? So once we go through all these steps, safety, intelligence, and certification, so we can talk about distributed intelligence, right? Because we can scale the technology, we can have many of them. We can talk of distributed intelligence, we can do collaborative tasks, we can talk about robustness to single point failures, because if you have multiple vehicles and you lose one of them, they should be able to reconfigure the mission. And we can even touch the e-commerce, and here is one of the projects of our recent NSF awards for using drone network for parcel delivery. The last mile problem is known to be kind of the billion-dollar challenge of the parcel delivery industry. So when Amazon said they can use drones to deliver parcels, UPS, FedEx, and others starting optimizing drones with their delivery trucks. What we said it might be smarter to use ride-sharing vehicles in the road and pair the drones with ride-sharing vehicles, like they drop and pick up, and the vehicles have nothing to change in their path as long as they have signed up to be on that network, like Uber drivers. When they leave their home and they are on Uber, they turn on their phone and they become available to the network. So if we know where are the vehicles that are available for the drones to pick up and take off, so we can basically eliminate even the delivery trucks, have traffic is an but we have to optimize over random networks. So this is a challenging problem, how to optimize over random networks, how to do risk-sensitive rendezvous with these vehicles. This is a joint NRI with Stanford. So, and here is an example demonstration for the Chicago area, how you can drop on a vehicle, pick up from another one, and solve the last mile problem. So the big framework looks a little bit fancy. There are different problems here involved, but one of the problems that my student has recently worked on successfully is this risk-sensitive rendezvous. So, for example, the point of no return. So the drone is the blue one and waits for the car to go along that road. So say he has the information that the car will go, but he estimates that the meeting point would be the center of the SIA, but the car may change its path on its way, right? The driver may change his mind, so he's waiting a bit to take some data by the time that there is the point of no return, so that you identify beyond which your risk is kind of minimized. So we look into this risk assessment of this type of delivery tasks, and a paper is submitted to WOL for 2020. And as I started this talk from that feeding the 10 billion in 2050, so in Midwest we have lots of cornfields and we have lots of soybean fields. We collect lots of aerial images and we analyze to help the farmers to find the spots that need immediate attention, that need replanting, need more water, need disease prevention, and so on. And this is a nice workshop that got accepted in CVPR 2020. I mean, this is co-funded by my company, so that supports the workshop as well. So we're heading towards the fourth industrial revolution, where we need kind of to understand very well what are the challenges coming our way, right? It's about the safe intelligence, it's about human and robot pairing, and this human-robot pairing happening on all the levels, from the ground vehicles to aerial robots. So we need already good integration and good understanding of multiple disciplines, so we can't just work in one discipline. And while I briefly touched here upon a number of problems, obviously many problems remain, many more will reveal themselves as we start working across the disciplines. As we work with psychologists for a few years, we learned so much about psychology, and we understood that there's lots more to be learned to understand how to operate these vehicles around humans in different contexts. And obviously new architectures will need to be conceived, requiring new paradigms for B&B. This is a count-based chart that shows the evolution of the drone technology from different industries, retail and warehouse, last mile social, personal drones, and service consumer. And I mean, I had this quote a long time ago. This is already 2020. I'm not sure if it's already the 100 billion market, but obviously we'll get there as we see more progress in this area. These are my collaborators. collaborators on the types of problems that were included in this presentation, which was more the robotics related work in our lab. Some of my students, postdocs, alumni, my current lab, right? Partially, of course. Test pilot school where the guys do these lots of awesome flight tests and we enjoy working with them. And our New York Times pictures. I think I fit into my 40 minutes as I was suggested to use only 40 minutes for the talk, and I'm happy to take your questions. I kept it light, no math. Questions? Okay, go ahead, Martha.
Thank you. It was brilliant and very informative. Let me bring the urban planner hat. I saw Marco Pavone there.
Right.
And probably that connects to the work that Emilio Cazzoli with Marco were doing in Singapore.
Might be.
I mean, the challenge. So I would like you, urban air mobility is everything to be done. When you speak about social aware mobility, that's a main thing. Then if we bring the density, the city density, the urban canyons, the urban texture, any light, it's not happening, but any light or any word you can tell us about the urban planning, land use, and role to connect with this phenomenon that is happening.
Well, I think what we have to do, we have to plan a bigger project to work together to address all these
I like
problems.
that answer.
Because, no, I mean, obviously, look, for us even to make that one paper with psychologists, it took 4 years of experiments, repeating, finding people testing, understanding what's going on, my students learning all this VR and psychology, them learning what we care for. Really getting interdisciplinary results is so challenging. It's one thing funding agencies talk and they give the money and then there are all these reports. It's another thing to go nail down the result where you can say, oh, what we have there, we have that human perception model of safety in the integral of optimal control problem formulation. And writing a path planning task with the perception of human safety and solving it. And I mean, getting these results where you can claim and get a paper published out of it that's truly interdisciplinary is very challenging. Now what you are saying, I think this work is getting to city planning.
Yes. Any connection with Singapore, because in autonomy, Emilio's company,
Right.
I was at the MIT at the time, Emilio was there. Literally, in Singapore, they were able to deploy the cars beyond the small campus experiment. And so many things happened just because they faced the challenge in practice in a controlled situation. So meaning the humans and the city, somehow the city is another.
Right, city, you can have no, I mean, the situation there is like this. With city, you have prior maps of the buildings and everything, right? You incorporate all these priors into building your best path planning approach. But then you have to accommodate these random pedestrians, right? That's why I showed how the drone could adjust its path around the humans in a city. But, for example, this perceived safety model, you can't update it because you can't do the test with VR while flying, right? These certain tests and certain data have to be collected. So the reliability of this data, how you do these experiments, and by the way, if you understand how these other disciplines are moving forward, like health analytics, psychology, right? They're coming up with more and more better sensors that can do more sophisticated tests. So to keep up with their development and to bring it all into your test and to update your these perception models and put it there. And on the other hand, you can be super conservative and avoid these human congested areas. And this has to come with a trade-off. And there's also a big difference. It's one thing we talk today about all that. It's another thing we talk about it in 20 years. When 20 years later, we will be the elderly ones. And we are developing this technology. We are a lot more comfortable with it. Then if today I go and talk to my parents about it, they get that scared there, right? So understanding that the next generation that are going to be the consumers of this technology are going to be more comfortable because they grew up with it, right? Today we have junior generation that does not remember the pre-internet era. I went to school, I defended my PhD with handwritten markers and typewritten dissertation. So I mean, there is this generational change that as we develop this technology and all the disciplines move forward and we keep up this big perspective over everything, later, years later, when everything becomes a reality, like that in that Cinderella movie, right, that you saw, it's a different generation that's going to enjoy the benefits of this technology, and that generation has grown up with a different education in a different reality, doesn't know what was the world before IoT, right? So today even for us, we become so IoT dependent, right? If something doesn't work a minute, doesn't connect well, we get frustrated. Imagine kids who have never lived in the previous era. So, I mean, it's very important to keep the perspective in a global sense, with account of all the disciplines, and with account of the fact that we are all human beings. We like to be mistaken, forgiven, and compassionate, and all that. So that's very important, the social setting of these problem formulations, that if it's society, then we're humans.
Thank you.
Right. More questions? I'm happy to send papers. Send me emails. I'll send you links. Yes, okay. Mhm.
I'm interested, like you mentioned about certification about data-driven methods and
Mhm.
control. So a lot of times, because it's data-driven methods, it's really hard to certify it. And even if you have a data set, data-driven people are really good at just like breaking the data set record. So like I'm wondering in the future, like what is your suggestion of a better method to certify the data-driven method? And if, for example, they give you a safety region of like 96%, would you be happy about that? Because
Okay, I got your question.
Yeah.
Let me remind you, the two crashes, the Boeing 737 this year. Why did they happen? I think the final report indicated the certification procedures were cheap, shortcuts, and they didn't go through every step, right? So anything that requires online software modification won't be certified. It's just not worthy thinking of a method that would have online software modification. The whole software has to be certified before the deployment. Okay, that's why, for example, doing sufficient number of offline tests, creating all the models, testing and so on, is very important not to face what happened with those two Boeing 737s this year, because I know a little bit more details, nothing that's outside the public domain. I just read all the reports. So the quick, cheap certification methods don't prove to have long runway. Okay. And what I learned from Louis Shaw, who is my colleague in computer science, he says any software that assumes online software modification in real time won't be certified. It's just, you have to accept it as an axioma. That requires clear understanding of how much work can be done before the deployment, so that the software you put there, it has maybe all the right switches, but it does not assume online modification of it. I don't know if over the years the certification authorities would like to relax some of these requirements or give us an easier life. The bottom line is that 737 will stand in the way, because it has been already proven that the certification was overlooked and some shortcuts were taken and it ended up with crashes. So lessons learned are very important, and that lesson will stand in the way. At least so far it's so fresh. I just know what happens. Okay, go ahead.
Just a small question about the Q-learning example you showed.
Which example?
The Q-learning example, the reinforcement.
Okay.
There's a drone here. I guess they will, in some degree, it will cooperate with the drone
Right.
in the lower
Low
altitude.
altitude.
And how they cooperate with each other? Is it a part of the multi-agent environment, or is serve as an external agent, or just taking image informations?
No, they take images, they communicate. It's the multi-agent environment.
So it's a multi-agent environment and taking different
Images and communicating. Right.
Okay.
Okay.
How easy was it to get L1 on the first aircraft? Did the US Navy, did they let you?
The first one, so at first we flew the UAVs of Naval Postgraduate School here in Camp Roberts, California. Those were the first flight tests. Then the next one we flew was the Boeing 757 subscale, 5.5% at NASA. I should say it was very easy as compared to all the other controllers that were in the same competition and race that NASA had. We went there first flight, boom, the second flight was already awesome. The first flight with some oscillations, we had to do some tuning. The second flight was awesome.
So you don't need any certification to deploy those?
No, these are research aircraft that are built to test. Like even we go to, say, Edward Air Force Base, they fly, they put this accident, but they are so sure that this VSS safety switch will come on, because how they train pilots, right? It's like the driver schools have cars with additional pedals for the instructor that sits next to you, can override safe. Well, they have to teach people to drive, they have to teach people to fly. They have everything built for that so that they can try different things. The pilot will try to recover, and they can collect the data and then teach the pilots, and it will be all safe, right? Otherwise, how they get pilot license? They have to go and demonstrate. So these aircraft are research aircraft. They are equipped with sufficient safety switches. If something goes wrong, if our controller could have not said, the safety switch will come on. So basic, but even before every deployment, they do 2 weeks of ground run tests. They just run on the ground, on the runways, test everything before they go up. But I mean, these deployments, I have to tell, it takes us 6 months from getting the model to the flight test. We go through multiple calls, sitting with generals and marshals who have to sign all these papers from 7 a.m. in California to 7 p.m. Till we go all the failure scenarios, what did we get in simulation, what do we do, till they sign off, we go through ground runs. So this is very rigorous process. This is not a joke. And going through all that and not failing all that to get the green light check for the flight test, it's a very useful experience, but you can't start today something new and hope to get it done next year. 10, 15 years of work, working patiently with, like, no shortcuts. No shortcuts, you go step by step, systematically. For me, it was very useful to understand and respect and learn the engineering rigor. Because my PhD was in math. I thought theorems is what's rigorous, and that's usually math. I thought engineering is all okay, experiments, who knows what. But going through this process and seeing this engineering rigor, I developed so much respect for all the pilots, flight test engineers, and everything. I mean, it's tremendous work, and it's very rigorous. So it has its own rigor and culture that one needs to learn, understand, respect, and live by those rules. And no shortcuts. They pay a huge price. So.
Thank you, Dr. Hovakimyan, for a fascinating session.
Thank you, thank you. So I fit into time, so I'm glad I made it. Thank you.
Yes.